Hey, I'm Sep, and I'm going to present the work with Cyrus Shahabi on theoretically analyzing learned database operations under distribution shift through distribution learnability. Um, Machine learning operations are being used to perform specific database operations in a lot of practical settings these days. Um, these approaches are shown to improve efficiency of database systems in practice, and they've been applied to various different database components. In this paper, we specifically consider three fundamental database operations that machine learning has been shown to improve its efficiency. One of them is indexing, which is the problem of finding the location of an item in an array. The second one is cardinality estimation, where we find the number of elements in a data set that match a specific query. And finally, sorting, where we are given an array and we just want to sort it. Learned models are used in all these scenarios to replace a specific database operations. And this roughly works as follows. We have some database operations, and we kind of try to black box it as this function f of t, which is a function that takes some input x, usually a user query, and outputs the answer from the database. So for example, binary search is such a function that takes a query and outputs the location of an item in the array. And we just kind of black box doing binary search, for example, and call it this function fd. A machine learning method learns a model that approximates this FFD. And this learning is often done through a supervised learning setting where we just collect different samples and try to make sure that F hat is similar to FD on the same outputs. And at query time, we just use this model that we learned to estimate the position of items in the array. So given a query, we just give an estimate, for example, of where the query would be located, the answer would be located in a dataset. Because it's an approximation, often there is a local refinement step that tries to make sure that we can obtain the exact result. And this is, for example, in the case of indexing, done by doing a local search around the model estimate to provide the exact answers. And this is shown to provide significant practical benefits experiment. One problem, however, is that as we insert new data, this ground truth function fd changes. And so as a result, the accuracy of f hat becomes worse, and we basically lose a lot of its practical benefit because now we just have a worse model to use in practice. This reduction in accuracy is worse if we have distribution shift, because this FFD changes in a way that accuracy of f hat would be different. And the common solution is in practice is to periodically retrain the model. The problem is it's computationally expensive, and ideally we don't want to do it frequently. So in general, there is problem of we need to understand why and when these learned approaches perform well when there's insertions and distribution shift. And especially important for practical deployment because in practice we do have insertions, and as we insert new elements, we kind of want to know how the performance is going to change in the future. So we want to have some sort of a bound on model performance as we do insertion. Experimental results also show that performance does degrade as we have insertions, especially a problem when there's distribution shift, and often results show that the performance can get worse than non-learned method if there is an insertion intensive work. There has been previous work studying the problem of theoretically analyzing learned database operations. We've specifically looked at providing theoretical guarantees on static data set and studying the model size needed for various database operations. But this paper is the first theoretical analysis of various database operations in the presence of insertions and distributions. I'm first going to give an intuition of our general analysis framework, how we approach the learned database operations, and now I'll give a brief overview of our results. We kind of see learned database operations following a statistical view of database operations. So what this means is that we basically assume the data is sampled from some underlying distribution chi, and when we're asking queries, we're basically asking for answers from observed values from this data distribution. So these values are sampled. So we have n samples from this data distribution, and we want to look at those and answer a specific query. If this data distribution is known, then for aggregate queries, we can use the expected query answers from the distribution to answer the query. And so this can be just done by calculating the probability of data falling in a specific range and using that probability to provide expected query answers based on the data distribution. In the worst case, there is well-established theoretical results in statistics that says query answer is going to be within O of the square root of n with high probability if we actually do know the data distribution. So given the data distribution, we can answer queries accurately to O of square root of n with high probability. And this is great because if the data distribution can be efficiently stored and evaluated, this means that we have an efficient way of providing query answers to a reasonable accuracy. Accurate queries I mentioned, we can formulate indexing, sorting, and cardinal estimation as a form of accurate query. So it's beneficial, this results for the specific queries, database operations I mentioned earlier. One specific problem, though, is that in practice, we don't know what the data distribution is. And so we need to actually learn the data distribution from our data set. And so learn database operations, learn a model of the data distribution to answer database queries using that model. And so we can further dive deeper into this specific statement I just mentioned. So we can kind of look at the database operations as performing two things. So we have this modeling step where we want to, given an observed data, we want to find an accurate and efficient model of the data distribution. And so this means we have n samples of the data distribution. We want to find model parameters for the data distribution where this data was sampled from. We formalize this notion of accurate and efficient model through a notion called distribution learnability, which can be studied independently of database operations. And basically, this notion helps us quantify the efficiency of modeling. It's very similar to statistical estimation, but we care a lot more about how efficient modeling can be done, both in terms of doing inference from the model and in terms of how we can build the model. But after we have this model, then we are going to use this model to perform database operations. So to basically give you query answers. And so there's this model utilization problem where, given the model of the data distribution, you want to provide accurate answers. And as I mentioned, you can try to do this by using the expected query answers based on the data distribution you've learned. Often in practice, this is a multi-step process where we iteratively refine our estimate after looking at data. So we kind of go back and forth between data and model. It's often not a one-shot process because we want to provide accuracy better than O of square root of n. So we can kind of do an iterative process and provide results to any arbitrary accuracy. And we need to be able to do this efficiently, we need to build data structures around models so that we can actually use models efficiently. And finally, we also have to account for insertion and distribution shift and figure out how they impact the model accuracy. So as we have new data insertions, then we need to analyze how insertions actually affect the accuracy of our model. And so we do that in our paper, and we provide a thorough analysis of the database operations by kind of looking at both the modeling problem and the model utilization problem. We provide analysis for various data distributions and distribution shift settings. Here, I'm just going to provide a general summary with interesting insights that our results show. And I refer you for the exact results to the paper. I do want to mention that our results are expected complexity, not worst case, because in the worst case, a lot of the non-learned operations are already worst case optimal. But as I mentioned, this statistical view and the distribution learnability framework allows us to study the expected time complexity of performing the operations. So for indexing, we show that a learned index can support insertions and queries in of log, and expected time. And this basically follows this general idea of building a model from the data and then using that model to answer queries. This log n roughly comes from the fact that we actually have to, every time we use a model, we can only do so with accuracy of square root of n. And so we use this result to build an efficient insertion and query algorithm that performs this in O of log n. The problem, however, is that this time complexity drops to the traditional O of log n when there is distribution shift. And this basically happens because when we do have distribution shift, this model we learned is not very good. And so it cannot really provide reliable query answers. And so it's kind of expected that the accuracy should drop down to O of log n because we can't really use the model of the data distribution we've learned. We also study cardinality summation. We show that we can answer to an error epsilon with O of 1 over epsilon lower space consumption than non-learned methods. And again, the framework is generally similar, but the main insight here is that you can use really small models to capture the data set's characteristics so that you can actually improve space utilization because these models are small, but still accurate enough to give answers. And finally, we study sorting, where we show that you can sort an array in O of n log n. The log n comes from similar reasons that we have it for indexing. But we also show that under certain conditions, you can actually sort your data in O of n. And specifically, this is when you don't need to perform this first step. So if you actually know the data distribution, we are able to utilize it to be able to sort an array in O of n. All these results I mentioned have extra distribution dependent factors that's hidden because of the big O. And to summarize, the results show settings where learned methods do or do not outperform non-learned methods. There's more detailed results in the paper, both regarding distribution, learnability, how we can perform the exact complexities of performing database operations, and also results justifying theoretical results for these common database design choices. So to summarize, we presented the first theoretical analysis of learned database operations. We showed novel characteristics of learned models, provided bounds on performance, and showed their advantages over non-learned methods. We also developed distribution learnability and novel theoretical tools that built the foundation for analysis of learned database operations. There's an interesting problem for the ML community here. So distribution learnability is something that requires a lot more studying, specifically for broader distribution classes and specifically consider computational aspects. There's also the notion of distribution shift that can be extended beyond the variation distance, total variation distance that we use, and also the independence assumptions that are used in our theoretical analysis. Thank you for listening.